Hi, I'm Mr. Kangas, and today we're going to take a look at Chapter 3, Section 3, and Chapter 3, Section 4. Together, they represent one-step equations. One-step equations are what they say they are. They're equations that take one step to solve. An example. We'll start with addition and subtraction. An example to start with would look like this. Many of us know what x is equal to because I chose a simple problem. And I intentionally choose simple problems when I'm introducing concepts because I want people simply to focus on the why this is working and the how this works. I don't want you to focus on the decimals or the fractions or the addition of large numbers. I want you just simply to focus on how to solve and why this works. So, before I get started, I want to point out what the word equals means. That equal sign is a big deal. And many people, when teaching math, forget to accurately describe what equals is. Equals is telling me that x plus 3 and 7 are the same thing. Literally, the same thing. A good way to look at it is the equal sign is telling me that Mr. Kangas, which is me, is the same person as Justin Kangas, also me. They're one and the same. The names or titles or values written here may look different, but they represent the same thing. The difference between equals and congruent, two terms often used synonymously or interchangeably, is that congruent is kind of like looking at a set of twins. They look exactly the same, but they're two different beings. So congruent means you have two separate things that look exactly the same, whereas equal is saying we have two things that are exactly the same. They are the same person, they are the same thing. They're essentially just different names for the same person is the way to look at it. Here's Mr. Kangas, here's Justin Kangas. What you do to Mr. Kangas also happens to Justin Kangas because they are the same person. They are the same thing. What you do to x plus 3 also happens to 7 because they are the same. So, our goal in this problem is to figure out what x is. If you were to put the equal sign into words, a word often used to describe equals is the word is. X is 7 means x equals 7, if x were to equal 7. So, right off the bat, I see my problem, and I know what my goal is. I know my goal is to get x by itself on this left side, because I want to know what x is. So that means this plus 3 is in my way. So how do you get rid of that plus 3 but keep the x? Well, you're going to do the opposite. Opposites cancel each other out. So the opposite of plus 3 is minus 3. And the reason I know this is going to work, there's two ways of looking at it. One, we know that naturally opposites cancel each other out. But two, if you start at any number in the world, add 3 to it, then subtract 3, you're going to end right back up at that number you started at. So for example, if I start at 8, and I add 3 to it, I'm at 11. Then I subtract 3, and I'm back at 8. So the plus 3 was undone by the minus 3 because plus and minus are opposites. They completely canceled each other out, but they didn't affect the x. They just affected each other. They canceled each other out. Now the problem here is this minus 3, this opposite that I input into the equation, okay, this was not up here in the original. I put that minus 3 there. Now in order to keep the equation equal, we also need to minus 3 from the other side, and the reason for that is something I was talking about earlier. Equals is telling us that the left side is the same thing as the right side. Here's Mr. Kangas, here's Justin Kangas. They're the same person. If you take $3 from Mr. Kangas, you've also taken $3 from Justin Kangas. There's no way around that. What happens to one side has to happen to the other side because both sides are the same person or they're the same thing. They just might look a little different right now because we don't know what x is. It's kind of like up here, we don't know what x is, so it's like if you were looking at half of me, you wouldn't know what the bottom half of me looked like. Over here, this is looking at all of me. You know the bottom half is there, you're just not quite sure what it looks like. So here's Mr. Kangas, here's Justin Kangas. We just took $3 from Mr. Kangas, and now we're taking $3 from Justin Kangas because they're the same person. If you take $3 from one of them, you're taking $3 from both of them because they're the same person. So to finish off, 7 minus 3 is 4. Now the cool thing about one-step and two-step and multi-step equations, something we're going to be getting, all the stuff that we're getting into, is when you get your answer, you can check it. X equals 4. Well, is that true? Let's go up here. If x was 4, then that means that 4 plus 3 should equal 7, which it does. So I have the right answer. Let's take a look at a couple more problems. They all typically function the same way. So if I have, well, I'm going to take the same, a similar problem. We're going to do 3 plus x this time equals 7. Okay. Now, before we said we were adding 3. So to get rid of the plus 3, we had to do the opposite and minus 3. Well, this time it's plus x. But we still need to get rid of the 3. Our goal is still to get x alone. So to do that, you're going to go about it in a very similar way in that you essentially are going to look at the sign of the 3. If the 3 is positive, you can kind of pretend there's a little plus here. If the 3 is negative, you can kind of pretend there's a little minus there. Okay? So if this is a positive 3, the opposite of that is negative 3. So you could do 3 plus negative 3. Or you could still do 3 minus 3. It'll still end up getting you the same result, but oftentimes when the terms are reversed, it confuses people. You can still do it in the same manner we did before, or you can say 3 plus negative 3. So like I said, it's not going to make a difference either way. We could still look at it as 3 plus, so we want the opposite, and so we're going to do 3 minus. 3 minus 3 is 0, plus x is x. And then you minus 3 on the other side as well. You get 4. So now we're going to take a look at a subtraction problem. If I have x minus 4, and let's say it equals 5. Okay, we have a goal of getting to what x is. We know that we have to get rid of this minus 4. Well, the opposite of subtract 4 is plus 4. Do that to both sides. We get x equals 9. And 9 minus 4 is 5. Now again, if you pick a number, you minus 4 from it, then add 4, you end right back up at that number. So let's take the 9 for example. 9 minus 4 is 5. Plus 4 is 9. So now at this point I'm going to introduce negatives. They don't really change up the process at all. But a lot of times when students or people are introduced to a problem that has a negative in it, when they're used to dealing with problems that have positives, they think something must work differently here. The problem must function differently, but the problem functions exactly the same way. The opposite of subtracting negative 4 is adding negative 4. So take a note here, the only thing that changed was the operation. The number did not. Minus negative 4 plus negative 4. Because the plus negative 4 is new to my equation, I'm going to do it to both sides. Here. So if you're adding negative 4 to Mr. Kangas, you have to add negative 4 to Justin Kangas, because we're the same person. And x is 1. If you have trouble adding and subtracting with integers or negative numbers, take a look at our chapter 2, section 2, and chapter 2, section 3 tutorials. And also, yeah, we'll just leave it at that. Okay. So those were examples on adding and subtracting with x. The next group of one-step equations will be with multiplying and dividing. So it functions the same way adding and subtracting do. Multiplying and dividing are opposites. My goal is to get x by itself. And right now I need to get rid of that 3. That 3 is being multiplied by x. So the opposite of that is to divide. So I will take my 3x and divide it by 3. I will take my 15 and also divide it by 3. And that gets me an answer of 5 down there. Again, if you divide Mr. Kangas into thirds, you have to divide Justin Kangas into thirds because they're the same person. You can't divide one into thirds without dividing the other into thirds. So some of us may be looking at this, might have been a little easier to grasp why adding and subtracting cancel each other out. However, here it functions exactly the same way. So for example, if we gave x a value, let's say x had a value of 5, as it does down here. Okay, 3 times 5 is 15. Divided by 3 brings you back to 5. 3 times 2 is 6, divided by 3 brings you back to 2. So the division of 3 undid the times 3. And also, just as it works with division, with adding and subtracting, if you have a negative 3 that's being multiplied, you also need to make sure that when you divide, you're using that negative 3. Because, again, the operation changes, the number does not. If that number is negative to begin with, you need to make sure that when you go to get rid of it and you divide by negative 3, you're dividing by negative 3. A common mistake is that people divide by positive 3. Now, if you take a number such as 5 again, if I do negative 3 times positive 5, I get negative 15 for my answer. Divided by a positive 3 would get me a negative 5 or a negative x. I don't want that. By having that negative down there, 2 negatives make a positive. Just to show you that, negative 3 times 5 over negative 3. Negative 3 times 5 gets you negative 15. Negative 15 divided by negative 3 gets you a positive, which is what we want. Alright, last problem before we're done. Do an example that has division in it. We have x over 3 equals 5. I know I want to get x alone, so I got to get rid of the divide by 3. The opposite of divide by 3 is times 3. Going to do that to both sides. And the only reason why I put this 3 here over 1, I put it in fraction form, is because my x over 3 is technically in fraction form. So it's a little easier to comprehend when things are in the same form. But just as all the other ones we've done so far, it works exactly the same way. If I pretend that x is 15 and I divide it by 3, I'm going to get an answer of 5. And then I times it by 3 and I'm going to be back at 15. Okay? In other words, x. So the multiplication undid the division. The division happened, brought me down to 5. The multiplication undid it because their division and multiplication are opposites and brought me back to the 15. Another way to look at it, for those of you who understand fractions, you would know about cross-canceling. Okay, cross-canceling is like reducing diagonally, and it can only be done when you're multiplying fractions. So 3 goes into 3 once, and 3 goes into 3 once. You find a number that goes into both of these numbers diagonally, which in this case is 3 because they're both the same. X times 1 is x, 1 times 1 is 1. Either of those explanations work for why it is x is alone. So, I think the simplest explanation is if I take a number, divide it by 3, and then multiply it by 3, I end up back at that number. That's going to work the same for any number in the world, no matter what it is. And I get a final answer of 15.